In this chapter, we are mostly interested in working with fractions, and in fact, we'll be performing the 4 fundamental operations on fractions. That's adding, subtracting, multiplying, and dividing. Before we get into that idea, though, there are a couple of techniques that are helpful to us, and one of them begins with a discussion of multiples. Now, the multiples of a number are generated by taking a number and multiplying it by 1, 2, 3, 4, and so on. So if we want to generate multiples of 4, it would be 1 times 4, 4, 2 times 4, 8, 3 times 4, 12, 4 times 4, 16, 5 times 4, 6 times 4, 7 times 4, and so on for the multiples of 4. For the multiples of 6, same idea. It's 1 times 6, 2 times 6, 3 times 6, 4 times 6, 5 times 6, and so on. Now, in the lists of multiples for a couple of numbers, you occasionally see that the multiples are the same in the two lists. That is, for 4 and 6, 12 is a common multiple. And as we go along, we see another one here. We see 24 is a common multiple. And there would be others as we would proceed on with the list of multiples. Occasionally in dealing with fractions, we want to identify the least common multiple that a couple of numbers have. And we could certainly do that by writing the list of multiples for the two numbers and then just looking at the list and picking out the smallest common multiple in the list. But that's somewhat impractical when the numbers get rather large. There is another way, and that way involves looking at the prime factorization of the two numbers and just picking out certain prime factors. Let me show you what I mean. The prime factorization of 4, since 4 is 2 times 2, we can write it as 2 squared. The prime factorization of 6 is 2 times 3. Now, the least common multiple will involve every different factor that we see in these two prime factorizations. And that kind of makes sense, doesn't it? Because after all, we're talking about multiples. Generally, a number is bigger if it's a multiple, you see. It's the only one that's the same is the very first one in the list. But generally, the multiples of a number are bigger than the number that we start with, and therefore it should make some sense that it would contain the factors, you see, all of the factors that we're talking about. All right, and not only that, but when a factor is the same in both prime factorizations, we choose the exponent on that factor to be the largest of the exponents in the two prime factorizations. So we would choose 2 and 3 as the two different factors here, and we choose 2 to appear twice. That is, it has an exponent of 2 on it. So 2 squared times 3, or 12, is the least common multiple as we expected. Let's take a couple of examples. Suppose we want to find the least common multiple of 450 and 600. We first perform a prime factorization on 450 and 600. We did that earlier, so I'm pretty confident that that part of the problem we can deal with easily. But 450 has this as its prime factorization. 600 has this as its prime factorization. Now, one peculiar thing about the two prime factorizations here is that they share factors. That is, 2, 3, and 5 are the factors involved in both of these numbers. That's a pretty unusual circumstance. But the idea for least common multiple is that the least common multiple is going to involve every different factor that we see. We see 2s, 3s, and 5s. So I'm writing a 2, a 3, and a 5 here. Now the trick is to identify the exponents on the 2, the 3, and the 5. And to do that, we just select the largest exponent on those shared factors. So here the exponent is understood to be 1, here it's 3. We choose 2 to occur as a factor 3 times in the least common multiple. 3 appears once here, twice here, in the least common multiple, twice. 5 appears twice here, in the least common multiple, twice. So we have, let's see, 2 cubed times 3 squared times 5 squared. We need to multiply this out, and when we do, we find the least common multiple to be 1800. Let's go through the process again. We want the least common multiple here of 20 and 525. The prime factorization of 20 is 2 squared times 5. The prime factorization of 525 is 3 times 5 squared times 7. Now, when we identify the least common multiple, the first thing we want to do is identify all of the different factors that we see in the two prime factorizations. You see, the different factors are 2, 3, 5 is shared, and also 7. So we have 2, 3, 5, 7. And now it's a matter of what exponent will appear on each of these. Well, let's see. For 2, let's see, 2 appears twice here, so the largest exponent on 2 is 2. For 3, 3 appears only once, and it appears right here, and the exponent is understood to be 1. For 5, 5 is a shared factor. The most number of times that 5 appears in either prime factorization is 2, so we list 5 squared, and 7 makes its appearance here, so it is to the first power, or 7 appears as a single factor here in the least common multiple. Multiplying these out, we get, let's see, this would be 4 times 3 times 5 squared is 25 times 7, and expanding this, we find the value to be 2100. Now, let's shift our thinking a little bit. We were talking about multiples before. Now let's talk about factors. Now, in the last chapter, we talked about factors and divisors as being pretty much the same thing. When we're identifying factors, we're identifying divisors. When we're identifying divisors, we're identifying factors. Okay, I've listed here the factors of 24. Now, it's handy to realize this relationship between factors and divisors, because we can just look at 24 and say, gee, what numbers go into 24 a whole number of times? And then we're identifying the factors, you see. So 1 goes into 24, 2 goes into 24, 3, 4, 6, 8, 12, 24. 24 has an awful lot of factors. And so does 30 for that matter. Here are the factors of 30. These are also the divisors of 30. Now, in the business of working with fractions, sometimes it's necessary for us to identify common factors, and in particular, the greatest common factor. Now, the common factors are found by looking at the list. We have 1s, we have 2s, we have 3s, and we have 6s, you see, as factors that are common in both of these lists. The greatest common factor, the largest of these common factors, is the 6. Now, once again, there is a way to identify the greatest common factor by using a prime factorization, and here's how that works. 24, the prime factorization is 2 cubed times 3, and for 30, it's 2 times 3 times 5. Now, it should make some sense that if we're looking for common factors, you see, for the greatest common factor, that we would identify the factors that the numbers have in common. So let's see, the common factors, 2 is a factor common to both of these, so is 3. So 2 and 3 are factors that they have in common. Now, how many times what exponent do we put on there? Now, I want to make sure we understand this, because before, for the least common multiple, it was the biggest exponent that occurred with common factors. But here, with the greatest common factor, it is the smallest of the two exponents. And here we have 2 appearing 3 times, and here once, so we use 2 as a factor once over there. 3 appears once here, so we allow 3 to appear once in the greatest common factor. So 2 times 3, or 6, is the greatest common factor, or the greatest common divisor, if we want to say it that way. Suppose we want to find the greatest common factor of 12 and 80. We look at the 2 prime factorizations, and then we look for common factors. All right, we pick out the factors that these have in common. Well, let's see, they both have 2's, and that's it. They both have 2's involved in them. Well, let's see, now, if 2 is the only factor that they have in common, how many times do we use that 2? Or what exponent do we put on the 2? Well, 2 appears as a factor twice here and 4 times here. We use the smaller of those 2 exponents. So 2 squared, or 4, is the greatest common factor for 12 and 80. And let's understand that greatest common factor means that this is the largest number that will be a common, not just factor, but divisor for these two. So it's the largest common divisor for 12 and 80 that we've identified here.